mind if I switch this off?
Oh, okay.
Okay, let's get going. So, of course, you'll soon start presenting, but I just thought I'll just remind you the rules of the game before you present. And this is, of course, something that is valid for all the assignments or homeworks that you have throughout the course. And you have already experienced it once, so this is your second homework. But just let me just brief you through. As you know, this is just a memory jog because I've pretty much mentioned all of these many a times. So this is essentially a team game, as you know. So I'm not going to be evaluating you individually. So irrespective of which problem you choose, and then you know that having seen this particular homework, each problem is of different complexity and involves a little more work. So which means that though each of you will be working on and presenting a particular problem from each of the sets, it's essentially a teamwork. So you need to be consulting with each other to ensure that all of you eventually contribute towards it, even though the presentation will be done by one. And essentially this is, I think, a part of the learning process, especially in dynamics. Unless and until we solve a lot of problems by ourselves, very difficult to get going. In fact, we used to have a dynamics graduate level course, which Professor Hodges taught us, and this was based on Kane and Levinson, which is a very, very novel and intriguing way to approach dynamics. These are essentially space dynamicists who work on very massive problems in terms of the number of degrees of freedom, and it makes it very difficult if you approach it through the typical classical textbook kind of an approach. So there's a very, very systematic way of doing things, and it's known as Kane's dynamics. The very method is known as Kane's dynamics, K-A-N-E, and his dynamics. And he used to give like almost like 10, 12 problems each day, each class, to solve by the next class. And it used to be quite a horrendous, because he used to not grade us for all of the problems, just he would randomly choose which problems he grades for. If that's one of the ones we had left out, then we get no marks, even though we might have done all the others properly. And eventually, even after I became a professor here, and then I asked him for the solutions for it, and he said, no, you have to do it all by yourself, even though you are a professor. So that's how we learned a lot of our dynamics in terms of trying to do problems by ourselves, however simple or however complex. I mean, it's a question of trying and getting there. And he would say that if you still don't get it, then meet me and talk to me, and then we will see how we can do it together. So that will be kind of the similar approach that I'll take, though of course the dynamics that we'll be talking about much simpler compared to Kane's dynamics in terms of the number of degrees of freedom involved. But once you get familiar with Kane's dynamics, which you will not in this course, but in case you happen to in a future course or by your own self-reading, which many people have done, then you will see that that's probably the simplest way to approach things, because it's very, very algorithmic in fashion, and something which is very catered towards computational implementations eventually, which is the way most realistic problems in aerospace dynamics will eventually get solved. But it's important to have an undergraduate basic course like this, where you tend to pick up the nuances of what each one of these concepts are. So conceptual learning is important. But as I said, the working of the homeworks is very, very important, and sharing and interacting with each other becomes really critical, so that you can see what somebody is doing wrong, or what somebody is doing right, which you might have thought wrongly, so that you essentially learn from each other, which is what I already mentioned in very first email, even before you left the US, that your competition is just yourself, your past self, and none of your own teammates. So you're all doing something together, and therefore there are certain tips that I can give in terms of the strategy for the game that you're playing over here in levels. As we get more and more complex problems, not necessarily complex in the sense of difficulty levels of doing it, but you'll be incorporating more and more concepts, because we'll be learning those concepts as we go, and those concepts will be reflected in your homeworks as well, so therefore it becomes a little more involved. And as I said, for all problems, not just the ESOP story, but for all problems throughout this course, I would strongly encourage you to use the current tools that are available, including the AI tools like those based on the large language models, any apps that are there. I know there are quite a few apps which provide solutions for various textbook kind of problems, various other problems, both in terms of professionals, some of them paid apps, and some of them, of course, free apps where your peers, other students or senior students who have already solved those problems essentially share. Since all of us have access to these kinds of things, I'm not averse to you looking at them and trying to get information from them. That's not the important point. It's kind of moot. What is more important is, do you understand the procedures involved? So that's why not only LLMs, but apps, internet, all kinds of sources, your forums, various discussion forums that are there. There's some very good discussion forums for mechanics, many of you might be aware of. Then, of course, friends and foes, if you do have any foes. Then I also want you to kind of cite those, because it's very important for us to learn together. And I'm looking forward to you citing where you got some information from, or where you tried to do it, and maybe you are successful, they're well and good, but if you're not successful or partially successful, how did you make certain alterations to that methodology? Let's say an AI tool gave you, or let's say some other information from some other source gave you. How did you, till where did it take you, and where did you go beyond that, and how did you go beyond that? The how is much more important. So that's why I want you to cite those sources, either written, or if it's on your presentation, or at least orally. If you have, let's say, forgotten to write, or it takes too long to write, you can just orally mention those things while you are talking, while you're giving your presentation. The other thing is, of course, in contextually, it's not put all of the citations at the end of the presentation. We don't know where what belongs. So as and when you talk about something, then you say this is where you got the information from, and this is how useful or valid it was, and how did you add value to it. Then the next thing is in terms of their specific input or utility. I already mentioned, and most importantly, their limitations and how you kind of overcame them for with be it the LLMs or any of the resources that you otherwise came across. Then one of the things that I have learned in my whole career of about almost 2.5 decades of teaching is that the best way to learn is to teach, and especially teaching brilliant kids like you. Essentially, you try to explore things from different perspectives. Even if you think you know everything, you essentially start looking at it from various different perspectives, and then you recognize there's so much more to learn. Learning is something that's a lifelong task, and those who stop learning are like dead men walking. So that is very important, to keep understanding that how much ever we learn, we only recognize how much we do not know. And then the internal problem allocation, because like for example in this previous set, I gave you 2 sets, A and B, and each of them had 4 questions, and between them you had to decide who works on what. So the basis for who works on what should be based on what you already talked about in your first assignment, Aesop's hare and tortoise, core competency. So you essentially see who is better at doing what, and then you within yourself, that way you know the strengths and weaknesses of other teammates, and then you try to pour in your resources in such a way that within the time 3 or 4 days that are left for the presentation, how you can probably leverage all of that and eventually do the best job. So between you probably know certain things about yourselves, having been classmates for 2 years or so. So you know who is good at what, and doesn't mean that the other persons are bad at that, just that they are probably picking up the nuances, and the others are probably a little more advanced in terms of the exposure that they have got. So, but you are a team, and that's how the team works in terms of leveraging all of your strengths synergistically. Then in terms of, as I already mentioned, I'm not going to be marking this for any individual scores. So it's very important that you don't be bothered about that. Be more bothered about, as a team, how you're presenting solutions for the entire set of questions. So then, because each question has some additional information over and above what I'm teaching in the class, so that it's also part of the learning process, as I already mentioned. And most importantly, this is not goal oriented, which is why I'm giving the answers for each of the questions. So you see in the problem set, you will see the answer, final solution, final answer to each of the questions, if it's numerical, or even if it's match the following or fill in the blanks, or which is not there in your first set. But if you're looking at even true or false or things like that, I will still give you the answer. But because for me, it's not the final answer that is important, it's the process with which you arrive at that answer. How, why? That is what is much more critical, because that helps you to tackle more problems of different kinds, maybe having certain similarities with the problems that you have already tackled, but it could be entirely new, but still all that experience really helps in how you tackle any new problem that you encounter. So then, as I said, because of this fact that we are more process oriented than goal oriented, I want your slides to predominantly be just skeletal prompts. It's okay, whatever you have designed for today, that's fine. I'm not talking about that, but maybe for the future assignments, maybe we'll have about 15, 16 more assignments. So all of that, you're looking at designing the slides bare minimum, so that you're essentially having skeletal prompts there. I would like you to generously use the whiteboard and or orally. Yeah.
We didn't make a slideshow. We were always going to do our explanations on the whiteboard.
Oh, excellent. This is precisely what I wanted without even asking for it. A teacher can't be happier than this. Thank you. So that's good. That's good. So, it's very nice. So, I mean, if at all you need to utilize slides, I'm saying that keep it minimum. But I'm really glad that you're doing it entirely on the whiteboard. In the oral description that you do, as well as the whiteboard description that you do, I do not want you to skip any steps, however silly or simple it might seem. Think of me as a Dumbo watching the presentation over here. Maybe my student slightly better than me, but try to explain each step by step, because that's how I understand how you know whether it's being done properly or not, right? So, so don't skip any steps. So even if what you have written down, you might have skipped steps because they're kind of obvious to you, but what's obvious to one may not be obvious to the other. So it's always good to explain that from that perspective. And finally, this is one of the most important things as part of the learning process, that when you're moving from one step to another, leave alone things which are too simple, but whatever new step you go to, there usually is some assumption involved. So rather than, just like I said, don't put all your citations at the end or references or bibliography at the end, state it where you get. Similarly, in terms of the assumptions involved in moving from one step to another, I want you to state it at that particular point when you're invoking it, okay? And since we are recording it, I would like you to keep the microphone as close to your mouth as possible because there's a lot of noise in the environment, and speak as loudly as you can, okay? Go ahead. Who's number one?
Do you have a marker? Oh.
Sure, you could flip it onto your shirt.
Okay. So whenever I'm given a problem, I like to write what I have and what I need. So for problem 1, you're given that a vector L is 4.7 t squared, and then negative 7.9 t with the units kilograms meters per second. And then we want to find, the goal is to find the magnitude of the rate of change of L with respect to time at t equals 2.8. So the first step is finding the rate of change with respect to t. So dl dt equals, so derivative 4.7 is just 0, it's the constant.
Just not skip any units, even in between, t equal to 2.8 seconds. So just...
oh, sorry, yeah. So, yeah, the rate of change. So 4.7, the derivative of 4.7 is 0. This is a constant. 4.7 t squared by the power rule would be 2 times 4.7, which is 9.4, and then t. And then the derivative of negative 7.9 t is just negative 7.9 by the power rule again, and then the units. And then we want to find the magnitude at time t equals 2.8. So first we would plug in 2.8, so dl dt at t equals 2.8 seconds. So there's no t in the first, the I unit. There is a t in this, so you do 2.8 times 9.4, which is 26.32. And then there's no t in the third term either, so this just stays negative 7.9. And then the last step is to find the magnitude. And to find the magnitude of the vector, of any vector, you do, so dl dt at t equals 2.8 seconds. And so the magnitude is the square root of all of the terms squared. So 0 squared plus 26.32 squared plus negative 7.9 squared. That equals, that all comes out to 27.48 kilograms meters second. Okay, yeah. And I believe that's the answer that you have written.
Are you sure about the final unit?
I guess the final unit would be second squared. Yeah, because I forgot because when I take the derivative, the second squared, yeah. Sorry.
Excellent, yeah. Did you use any resources or you probably didn't need it?
Not for this one, yeah. Okay.
Thanks, next. Anybody has any questions for him? Yeah. Clear, right? You can clip on now.
Okay, so problem 2a, the problem for me was we set v is equal to, which is the velocity vector of a particle is given by v naught e to the negative t over tau. And then you have the vector sine of omega t I hat plus cosine of omega t j hat. So v naught was given us to be 7.0 meters per second. tau is equal to 4.9 seconds, and omega is equal to 3.1 radians per second. So what it was asking was to find the acceleration. The magnitude of the acceleration at t is equal to 7.4 seconds. So to do this, you set acceleration. So I said the acceleration vector is equal to d v dt. Since this is a lengthy expression, what I did was distributed this first term to both the I hat and j hat vectors, and also plugged in.
Sorry for being a little picky.
Oh, no worries.
I know you know, aware of it, but v is also a vector, just like you put a as a vector. So
Yeah.
even in that dv by dt.
There we go.
And one of the things that we looked at in the very second class is when you're taking a derivative of a vector with respect to a scalar, the frame is important. So you put a frame, you mark your I and j.
So
Yeah, you just draw a sketch of two, on the left hand side, yeah, as a superscript. You just call it some frame A or whatever. Yeah, some.
okay.
You draw your I, J, and you call that frame in which they are fixed as some frame A.
Okay. So A, let's
May look
define.
like these are unnecessary for this problem.
No,
but,
no, it's-
this good practice will help you in future problems as we get into more complex stuff.
Okay. How about? Okay.
Yeah,
So
the
it,
A comes before the D as a superscript before the D, and more like a prescript.
right here. Okay.
Text.
That makes sense. Okay, so what I did was plugged in these numbers and distributed. What we get here, or actually, first, let's not skip any steps. So first, I'll write velocity vector as 7e to the negative t over 4.9 sine of 3.1 t I hat plus 7e to the negative t 4.9 cosine of 3.1 t in the j hat direction. So this is the velocity vector expanded out and with these constants plugged in. Now you get the acceleration vector, which goes to be a really long formula. So what I'll do is write small, or I'll actually just break it into two lines. Negative 7e to the negative t over 4.9 over 4.9 times sine 3.1 t minus 4.9 times 3.1 cosine of 3.1 t, and this would be in the I hat direction, and then you also have plus.
I want to check the brackets. Is it okay?
So yeah, let's replace this by braces. So big brackets, braces, and then individual parentheses inside. And then we have almost identical. Okay. So this is the I hat term, and then this is the j hat term, and then if the problem statement gave us that t is equal to 7.4 seconds. So plugging this in, we get the acceleration vector is equal to negative 2.5359 meters per second squared in the I hat direction plus 4.07913 meters per second squared in the j hat direction. Taking the magnitude is equal, which the magnitude of the acceleration vector, as Kush said, is equal to these terms squared. So you have the I hat term. I'm going to call this alpha, and then this is the j hat term. I'm going to call this beta. So it's equal to alpha squared plus beta squared. And then simplifying this all, you get the magnitude of the acceleration vector at t equals 7.4 seconds is equal to 4.803 meters per second squared. Okay.
Do you happen to use any resources?
I use the calculator to simplify the answers, but that's
Okay.
it.
The integrations, everything you did it from memory.
It took a bit, yeah. But yeah.
Okay, thanks. Thanks. Next question. Back.
Okay, for the premise for this question, it was a car moving at a certain speed and then applying the brakes for a couple seconds, and then the velocity decreases. So it was asking how much time does it take for the car to reach its original velocity after acceleration. So they gave us that the initial velocity, is this big enough? Or?
Yeah.
Okay, 60 miles per hour. And the time that the car was on the brakes was, so I'll call that delta T1 for the first part of the trip, and that was 3 seconds on the brakes, and that it provided a deceleration of 5.2 feet per second squared. So I'm going to say that's negative 5.2 feet per second squared as the velocity is decreasing. And they also said that the acceleration after was 2.3 feet per second squared. So firstly, I want to get everything in the same units, so I'm going to change miles per hour into feet per second. So if I do the dimensional analysis here, so 60 miles per hour, 1 hour, 60 minutes, and then you can do 1 minute is 60 seconds to get the seconds, and 5,280 feet are in 1 mile. So then we equal, it's 88 feet per second. And since it's constant acceleration for both parts of the trip, I can use the kinematic equation V final equals V initial plus A times T, A being the acceleration. So I named the first part of the velocity that occurred from the brakes as V1. That's our V final in this situation. And then we have V initial plus A1, because that's the deceleration, times delta T1, which is the braking time. And plugging that in, we have for V1, V initial is 88 feet per second, plus A1 is negative 5.2 feet per second squared, and then 3 seconds for the delta t. Putting that in the calculator, you get 72.4 feet per second. So that is the speed the car decreased to after the 3-second window, and now it's going to increase. We can use the same, this equation because of constant acceleration. So we have V2 equals V1, 1 being our initial, 2 being our final, plus A2 times delta T2. And our V2 is our original velocity of 88 feet per second. And our V1 is 72.4 feet per second, plus A2 being 2.3 feet per second squared. And our delta T2 is what we're solving for, because it's how much time it takes for it to pick up speed. And then solving this for delta T2, we get 6.78 seconds. And yeah, that's pretty much it. Yeah.
Would you like to comment anything on any resources you used? Or?
For this question, I didn't really use anything, just calculator. Yeah.
Use the microphone.
Okay, so this morning I found out the way I did this problem was wrong, but it's okay. I'm gonna just show you guys the way I thought about the problem. Okay, so the car's initial speed is 81 miles per hour. And it decelerates to 53 miles per hour in 4.8 seconds. And we're trying to find the distance it covered in that time. So basically what I did was I converted 81 miles per hour to 118.8 feet per second and 53 miles per hour to 77.73 feet per second. And then I took the difference of those two numbers. And then I divided the difference by the time. Which gave me the acceleration, which was 8.56 feet per second squared. And then I used this kinematic equation to get the distance. So velocity times the time plus 1/2 the acceleration times the time squared, which gave me 471.63 feet. 471.63 feet.
Okay, so what? We of course discussed this.
Yeah.
So can you now explain what's wrong with this approach?
Okay, so what's wrong with this approach is that the acceleration is not constant. So I can't use this equation because it assumes that the acceleration is constant. So the appropriate method to go about this would be to use,
Not only that, but one more equation as well, which you'll use just above that. The difference between the velocity and divided by time.
yeah,
So giving the acceleration, that's also valid only when the acceleration is a constant.
yeah,
So both these are not valid, right? So,
yeah. So-
have you given a thought in terms of how to do it?
So basically, how I would get the velocity at time t would be to take the initial velocity, which would be 118.8 feet per second, plus the integral from like 0 to 4.8 of the acceleration, I think.
Yeah.
I just didn't know how to formulate
All right.
this part.
So as I said, this is a teamwork. So anybody would like to fill in and probably try to complete this. So what is given in the problem, you probably have already read it, you have it in front of you, is that the acceleration is proportional to time. Okay. So unlike the problems that we saw in the previous three, where you could just use acceleration as a constant value. So these equations that she's talking about, v is equal to u plus at or d equal to vt plus half at squared, that you're familiar from high school physics, essentially when a is a constant, right? So what she has written is correct over there at the end, which is essentially an integration of the definition of acceleration as the time derivative of the velocity, right? So now can you probably take over and try to see if you can solve it. Any of you, any one of yours. It's okay even if we mess up things, but it's part of the learning process, as I said. So let's try and.
The integral of a of t, just like by definition, is b of t, right? So would you do evaluating the integral of a of t would be v of t from like with the bounds of 0 and 4.8, but I don't know if that's going.
Yeah, it's awesome.
No.
No, but then I don't think you
No,
can
A
use
is
that.
given to be proportional to time, right? How can you mathematically represent that?
Oh, yeah, exactly.
Yeah.
So the integral of at would be
T. Wait. It's proportional to t, so that's like multiplied to the.
Would it just be TAT?
No, it'd be multiplied to the velocity.
So that proportionality constant you have to find out. And it's also said that, see, typically any linear model is applicable, but it says that it begins with zero acceleration, which means that there's no constant term. It's not like it's an a naught plus b naught times t. It's just a b naught times t, or whatever they want to call that constant, right? So you have to determine that constant, and then what about this particular equation? If this is valid only for constant acceleration, do you remember how this was derived in high school physics? It's very similar to what you have here. Here she is writing v minus u is equal to v minus u divided by t is equal to a. So that is okay as long as a is constant, but v minus u by t that we are talking about here is actually dv by dt. Right? So in your actual problem, so we need to tend to write the actual acceleration once again, just like what you did over here, as proportional to d v naught times t. Similarly, you need to write a v naught times t there and try to integrate. So essentially, one integration is involved with this, and two levels of integration are involved.
Yeah.
So, which is why you got a linear model in t over here, because you're integrating a constant with respect to time in the high school problem. Whereas you integrate it twice, a constant, it becomes a quadratic. So that's why you got the t squared. So essentially you need to do that. Any volunteers to go ahead and try it out?
So you
Even
said
though-
that rather than like instead of being 1/2 AT squared, it's just AT in this.
Exactly. No, just start with always start with the basics, the definition, which is dv by dt equal to a. Okay. And your ds by dt equal to v.
Yeah.
Right. So therefore your d squared s by dt squared is equal to your a. And if a is defined as a function of time, then it's very easy to go ahead and integrate that. Okay. The more complex problem where a may not be given as a function of time, but might be given as a function of distance. Let's say I'm not accelerating by a certain amount after reaching a particular point in time, but after reaching a particular place. Because I know, let's say, the speed limits in this place are so and so, speed limits in another stretch are probably higher, and once I reach that point where that range is starting, I might accelerate to get to the higher speed which I'm allowed to legally, right? So that's essentially the process. So this is a very, very simple function of of time, that a is in this case is just some constant b naught times t. So I'm just a question of determining that. Can any of you want to give an attempt to that? You can write down the question and then maybe from that you can take it forward.
I was wondering if 8.56 could be the constant that right there, because
Yeah.
can't we?
Just come and explain. Just write down the problem and just let's go in steps. Let's
I'm not
not.
sure how to solve it.
Because when I was trying to resolve the problem,
Yeah.
I was like, I don't know how to formulate
Right,
this
right,
without
right.
without trying to use that.
Wait, so this is
But
my fault.
as I said, this is also wrong. So
Yeah.
that was not working. Yeah.
So is acceleration 0 when it's 5:53,
Yeah.
right?
Can you interpret? Can you one of you read that out? And maybe you can use the microphone, whoever is talking, and then. Again. You can use the microphone and read it aloud. And
I'll walk you through. So A of t is given to be proportional to time, right?
no, it doesn't take the audio from there. It takes only the audio.
So A of t is given to be proportional to time, right? How do you represent it mathematically? Okay.
Yeah.
Now if you substitute in that equation and integrate, huh?
So you can use the mic. Both of you can be there. Use the mic.
Also, wouldn't the initial be 81? It would actually be this because it decelerates.
Siddharth, you might
So-
want to use the mic.
So actually, I think this, I think this would be the initial because it said okay. Yeah, so it's decelerating. Okay, so 118 feet per second here. This would be after it's completed, so 77.73 feet per second. And then here we have 1/2 k 4.8 squared. 0 would just be 0, so you can just solve for k here. Oh, could someone put that in the calculator? Just subtract. So yeah. Sorry if I wrote it kind of messy.
Negative 3.565. I got that.
Negative what?
3.565.
5, 6, 5. So now we have the equation. So this is just negative 3.565t, and now we could put that here and get the. Wait, what are we trying to do here?
You're looking for distance. So.
Okay, so could we put this in something like this, or no?
No, see, even this equation is valid, as I said, only when a is a constant.
Okay.
So, but how did you get this? You integrated twice because.
Okay, integrated twice. Exactly.
Yeah.
That's
So
what I
because
did with a different
v is
question.
equal to ds by dt.
Yeah. So first, can someone put this integral here to get the change in velocity? Because that's
Well, you're just integrating negative 3.565t twice. Because that's acceleration. You integrate it once, you get v of t.
wait. Could you demonstrate that?
That's teamwork.
Okay, well, since acceleration is a function of time, it's not constant, so you can't use this. But you do know that, like some function of distance equals the integral of velocity, which equals the double integral of acceleration. So we just have to integrate this twice. So let's see, the integral of negative 3.565t, 4.8 equals negative 3.565 t squared over 2 from 0 to 4.8 plus, yeah, so you'll have like a plus c.
Yeah, so you have to be careful. It's what you've written on the top is a definite integral. So
Yeah.
integration constants.
Yeah.
So you have to use the information given to you to solve for the integration.
I don't
Yeah.
think you can. This is a small thing, but I don't think you can write it as a double integral because I think that's just something different.
Oh, yeah, it's just like conceptually. Conceptually.
LLMs won't understand that.
So yeah, the information you're given is that the initial velocity is what, 118.8 feet per second. So plus 118.8. Right? Is this correct?
No.
Here?
After this, yeah.
Well, I mean, this isn't part of
No, that isn't part
this
of it.
isn't part of the
Yeah.
derivative.
Oh,
Sorry.
yeah.
So I don't know what this is though. If someone wants to do that.
I can look
And then add the 118 at the end.
And that'll give us.
Velocity
Oh,
That gives us negative 41.47
plus 118.
plus 118 is 77.73.
Okay.
isn't that
That's what you just got. Okay, so
we just proved it. That's all we did.
we proved it. We messed up somewhere.
No, but that's supposed to be the answer. But we just have we're finding the distance, right?
Yeah.
So that's where I got confused. You said integrate again.
Well, you can't because it's not constant velocity.
Okay, wait. So we have the acceleration equation. So how do we get
Oh,
to distance?
I think you don't plug it in until the very end.
So you just integrate this again.
No. Yeah, so basically you just keep everything as a constant, or keep keep the variables here, and then just plug everything at the very end. So if you have here, give me. This is the eraser, right?
Yeah.
Okay, so I'm just gonna.
Erase like this.
Okay. So assuming that your so we have the supposed double integral of a t dt, right? So we have negative 3.565. So a of t is.
Pointed out that that's not the right way to.
Yeah, I know, but I'm.
Try to do it more precisely.
Okay.
Yeah.
So let's just do
You can do parentheses
one at a time.
outside of it. You
Yeah.
can do integral and then a parentheses.
Yeah, let's just do v of t is equal to that. A of t is equal to kt. So v of t is equal to integral of kt dt, which we get 1/2 kt squared plus our initial velocity, which I'm going to call vi. Then we get s of t is equal to the integral of vt dt, which is equal to the integral of 1/2 kt squared plus vi dt, which is equal to 1/6, right?
Yeah.
1/6 kt cubed plus vit plus
0 because
s
we're
of
starting
s of
with the
I
reference frame, I guess.
of t. So with our reference frame, we don't care about s of I of t. Oh, yeah.
Just
We don't care about s of I. So we get this is equal to 1/6 kt cubed plus vit.
let's see if I'm right.
And then plugging in k of t, which is that, and then t is, this is from 0 to 4.8. The 0 terms won't yield anything. So we have 1/6 negative 3.565 times 4.8 cubed plus 118.8 4.8 is equal to 504.5 meters.
No, feet.
Feet.
This is the solution given. That is the solution. Yeah. Thanks. Yep. Here's your calculator.
Thank you.
All right. Good job.
So let's move to problem set. So how did you manage it, Shadow?
I was so confused. I was like, because my best started just like 10, because like I seen the problem beforehand. I was like, okay, these don't look that hard. I have enough time. I was sitting on that one problem for like 4 hours, losing my mind. And just came to the conclusion that either I'm missing something or the problem is wrong.
I forgot that I was supposed to be doing number ones, and I started doing her problem, and I got lost too because I got her same answer, 471. I was like, what the heck? All right, so back to reality. This problem is pretty simple. So you're given two functions. One is a function of x for position, and one is a function of y for position. But in the problem, it actually only asks for acceleration in the x direction. So I'm just going to omit the y equation fully and just write down what we need. So we have x of t equals r naught cosine of omega t. And we want the acceleration, so we're looking for a of t. We're given r naught and omega, so we have r naught equals 6 and omega equals 5.128, units. Meters and radians per second. It's meters and radians per second. And so just plugging that in, because it's pretty easy, you get 6 cosine of 5.128 t. And then to find acceleration, you take the derivative twice by definition. So v of t is equal to dxt dt, which equals d dt of 6 cosine of 5.128 t. And you have to use the chain rule here. So you take the derivative of the inner function first. So we have, or the outer function, sorry, cosine. Derivative of cosine is negative sine. So you get negative 6 sine of 5.128 t times the derivative of the inner function, which is 5.128 t. So the derivative of this would just become 5.128. And so that simplifies out to negative 30.768 sine of 5.128 t. So that's v of t. And then a of t, similarly, is dv of t over dt, which is derivative of this whole function, negative 30.768 sine of 5.128t. Chain rule again, so the derivative of the outer function is derivative of sine, which is just cosine, so you'd get negative 30.768 cosine of 5.128t. And then derivative of the inner function again is 5.182t, or 128t, and then that's just 5.128. And so simplifying that, you get negative 157.78 cosine of 5.128t. And we're not done yet because this is an initial value problem where we're given t equals 1 second. So plugging that in, we'll get a of 1. This just becomes 5.128, so you get negative 157.78 cosine of 5.128. And that simplifies to negative 63.70 radians per second squared. I guess I wasn't really consistent with my units, but this here is in radians. This is a velocity, so this is in radians per second.
X is not in radians.
What is x in then? But the function is...
Because you put 6 in ahead of the cos, right? So that is in meters, not.
Oh, yeah, sorry. Yeah. Meters per second squared.
May not seem like a big deal here in this problem because all units are consistent.
Yeah.
But like in the previous problem, you had mixture of miles per hour and feet.
So when the units change.
It's always good to be consistent in writing the units so that you know if there is a change, then you can account for it.
Yeah. And then that's the answer, I think.
Okay, problem number 2 is kind of similar to the first problem. Okay, so they gave us two formulas. They gave us x is equal to r naught cosine of omega t, and y is equal to r naught sine of omega t. And they were asking for the acceleration along a specific vector. So what I did was, since these derivatives are a lot easier to compute, I kept the variables intact. So what I said was the x dt is equal to, using the chain rule, we get r naught negative r naught sine omega t times omega, and then dy dt as negative, or where is it? There you go. R naught cosine omega t times omega. And then we can take the acceleration by saying, okay, we want the acceleration to be dx squared over d squared t. Is that the correct way? It's flipped? Oh, okay. Like that? Okay, there we go. Is equal to negative r naught omega squared. And then this is with simplification. And then d squared y over d t squared is equal to negative r naught sine of omega t. So these are the acceleration components in the x and y direction, and we want a acceleration in a specific vector. So this vector I will call v is equal to, is given us to be, I'm going to write it like this, 0.6 I hat plus 0.8 j hat. So to do this, we know that to take the directional component along a vector, we do the dot product. So we get, I'm just going to write it as d squared x dt squared. I'm going to write this in bracket form. Comma dot vx vy, and then vx and vy are these two respectively. We get negative, all right, I'll just write it here, negative 0.6 r naught omega squared cosine omega t plus, or minus actually, minus 0.8 r naught omega squared sine of omega t. Now the problem gave us that r naught is equal to 14, omega is equal to 2.852. Can you give me the units?
Yeah. R naught is in meters. Omega is
Radians per second. And they give us t is equal to 3.8 seconds. Okay, plugging it in, we get the acceleration vector, which I'm going to call a, at 0.6 I hat, 0.6 j hat is equal to 100.71 meters per second squared. And this is the final answer. You can just place it down there. This is magnetic. You can just, okay, that's fine. All right, for this question, it was about the Falcon 9, and it had, it was basically, you can think of it as it was a rocket going up with the mass decreasing, so changing mass, so we automatically knew that's not constant acceleration. They even gave us an equation for acceleration that depended on time, so that confirmed that. Basically, the equation they gave us for acceleration upward for the Falcon 9 was t minus m naught g plus m dot gt over m naught minus m naught m dot t, and this equation makes sense because it's pretty much just net force minus the mass, which is the acceleration. The net force is the thrust upwards, and then this is just the weight, but the mass. This is the initial mass, and this is the change in mass, and then this is what that term for the mass is basically. And they gave us some values for in this equation. So like the thrust they gave us was 7,500 kilonewtons, which is just 7.5 times 10 to the 6th newtons. Then they gave us the initial mass, which was 550,000 kilograms.
which is just 5.5 times 10 to the 5th kilogram. And then G, as everyone knows on Earth, is 9.8 meters per second squared. And then the change in mass that they gave us was 2,500 kilograms per second. So what I did is I inputted all these variables into the equation for acceleration. And if you do that, so this goes 7.5 times 10 to the 6 newtons minus 5.5 times 10 to the 5th kilogram times 9.8 meters per second squared plus 2,500 kilograms per second times 9.8 meters per second squared times t, which that's what that's what we don't know. So we have, because it's a function of t, and then 5.5 times 10 to the 5th kilogram minus 2,500 kilogram per second times time. Yeah. So simplifying this further and not putting the units on here just to show like what specifically the values, you have 2.11 times 10 to the 6th plus 24,500 t over 5.5 times 10 to the 5th minus 2,500 t. So when you do all that math, that's what it comes out to. And this is our acceleration. We wanted to find the distance that it covered, similar to the previous question that Chanel did. What I did was the integral of the acceleration is just the final velocity minus the initial velocity, and I assumed that the initial velocity is 0. It didn't say anything about that. And then
This is typically a rocket which is launched from the
Yeah,
ground,
yeah.
so as you know, it's kind of strapped on.
Strapped on, so it'll have 0.
And, yeah.
Exactly. Yeah. And using my calculator for that, plugging that in, I got 1,504.6. So that means essentially that's the V final, 1,504.6. Oh, by the way, I did this from the time that they gave us, 0 to 134 seconds. And so this is the VF at that time in meters per second. And then V initial is just 0 meters per second. And then I took the indefinite, because there's that constant that comes out when you do the indefinite integral. So I did the indefinite integral using integralcalculator.net. And they gave negative 49 t over 5 minus 3,000 ln of t minus 220 plus c. So this is our v of t. So I'll just do v of t here, equals that. And since we know this is at t equals 134 seconds, I essentially solved for c. So v at 134 seconds, and plugging the t in here, when you plug in 134 seconds, you should get 1,504.6 meters per second. So solving for c, with that, you get 16,180.88. I'll get rid of the comma here. 1,180.88. And now we have the total velocity equation. Negative 49 over, sorry, mess that up here. Negative 49 t over 5 minus 3,000 ln t minus 220 plus 16,180.88. And then to find the distance covered, it's just the integral of the velocity from 0 to 134. And I put that in my calculator and got about 71,681.3 meters, and that's making into kilometers, that's just 71.68 kilometers, which is the answer. Yeah. Yeah.
So, once again, I think I got stuck with hardest problem.
Yeah, I don't know where. I didn't look at the problem and I saw there's 4 of them. I'm like, okay, 1, 2, 3.
Yeah, I looked at the number 4 and I was like, okay, this is simple enough. This doesn't look too it was that complicated. I also have conflicting answers, but we'll see. Okay, so mine is kind of like a duplicate of his once again. So the initial mass at takeoff is 550,000 kilograms. The burn rate is 250 kilograms per second. The thrust is 7,500 kilonewton, capital N, kilonewtons. Okay, so for the vertical acceleration, we can approximate it to be AYT equal to T minus MOG plus M dot G T over M minus M dot T. Okay, but after 60 seconds, it changes direction, so about like 45 degrees. So then there is now acceleration in the x direction. Please don't die on me, iPad. Okay, so I came here with a different answer. I talked to him and he had noticed that the acceleration was not constant and that we had to integrate. So that's what I was doing over there. And I redid the problem, but I still have conflicting answers, so I don't know if I did it correctly or not. But basically,
Feel free to intervene.
yeah.
Whenever necessary.
So basically, to like get the velocity for like for 0 to 60 seconds, I basically took just this equation. I'm not going to rewrite it out for the simplicity of space. I took the integral of this equation from 0 to 60, and yeah, and then that would also be the final velocity minus the initial, but we're starting from 0, so this cancels out. So this just gives you the final velocity, which I have to be, need someone to write this, 366.761 meters per second. And then I took the integral of this. Yeah, I took the integral of this from, because it changes directions within from 60 to 34 to 134 seconds, I took the integral of both of these from 60 to 134. So for the x direction, the initial velocity was 0 because it was just going straight up. So this gave me the final, which was 675.542 meters per second. And this one, it gives me the final velocity, but the initial velocity, at least from my understanding, should be this one because these are two different ones. Okay. So this equation gave me 591.032 meters per second.
So that initial velocity is only for the second one, not for the, you have two integrals there, right? One is along x and the other is along y.
Yeah.
So that velocity is along y.
Yes.
So whereas the x velocity is 0
Yes.
initially.
Yeah. So I add this to this one to get to basically get like the final y velocity. I do not have that written down. Okay, and nine, 5.792 meters per second. VF is equal to 675.542 meters per second. And it asks for the magnitude of the velocity. So these squared, and then you square root them. Guys, I have to give me a second to my calculator. Okay, so
It doesn't work out. I think you have to add the first one as well.
I have to add it to the,
Like,
This is
it's
it's added to that.
oh,
and that's
you already
this.
added it to it.
Yeah. It gives you a conflicting answer than the one on the paper, right?
Yeah, it does. So that's why I'm like, if you take the square root of them, it does not add up. It does not end up with 1.68.
Yeah. The only way you end up with 1.63 is if you add these two together, and then you take the square root of that.
And then you get that time.
Yeah, but that's not how you do magnitude.
So something else.
You do each of them. Wait, did you say you can square root each of them squared? Is that what you guys did?
You square both of these, and then you take the square root of it of the sum.
1.17
Yeah.
kilometers.
Um,
Which is also what I got when I did your problem. Let me see.
so the first integrals for the acceleration of the y.
Yeah, so this is from 0 to 60 seconds.
Yeah.
So this was like the initial velocity for this one, if that makes sense.
Did you like plug that into an integral calculator?
Yes.
And that's what it gave you?
Yes.
Okay.
And then for the x, it started off as.
It started off as 0, so there is no initial velocity.
You
Yeah.
have a final velocity for the x, and final velocity for the y shown below. Yeah.
Did we mess up somewhere in the process?
At least from what you explained, I think it was fine.
Oh, okay.
Unless some calculations in between were wrong.
Stage fuel burn rate is entered 2500 kgs per second over a maximum of 160 seconds. You're doing it for 60
Yeah.
plus
Yeah, that's
132. Okay, so I was not sure. Otherwise, they would have given me. I would have told it directly.
Oh. So mass initial is different at
That's
AXT
why.
Yes.
and then A-Y-T.
M naught changes to whatever the mass is at 60 seconds.
Yeah.
Because it doesn't.
So M naught is basically your initial mass, but at 60 seconds you've lost a bunch
Some
of mass.
Oh,
And
right.
you
So I
figure out
have
how much
to.
mass you lost, and then at 60 seconds,
So
that's
actually,
what you're
And at that point, it's constant mass, right? Or is there?
No, there's
No,
a
it's
new
still-
M naught.
It's still decreasing at a different
It's
rate.
still decreasing.
It's still decreasing at the same rate, except
Oh.
there's a new M naught, so you have to calculate that first.
Yeah.
That should give you a
Yeah.
larger velocity.
Yeah.
Thank you.
So you define that and not first.
Yeah.
I don't know.
Okay. So
550.
It's 2,500 kilograms per second times 60
It lost 150,000.
400,000.
Okay.
Yeah, so it's 400,000.
Not for AX and AY is 400,000.
Okay, can someone
And then
replug this into a calculator?
Sure.
Because that derivative was not fun. I mean, the integral of that was
but
not fun.
isn't the M naught? Didn't it say the M naught's only applied from 0 to 160, so it changes?
No, it says like the mass rate. Mass loss of mass.
Is it applicable as well?
M dot is.
Oh, M dot changed. Okay.
M
Yeah.
dot doesn't change. Which one are you doing? X or
I'll
Y?
do. Which one do I do?
I'll do Y.
Alright, I'll do.
T is 7,500. Kilometers. So. No.
But
M
M
dot
dot
is-
applies to the whole 160, right? So
Yeah.
since it's still within the range, I think it still counts, right?
So you're doing. Yeah.
But our equation was wrong because of that. How did I not?
750. Wait, no. This is M not dot. So 400,000.
For the thrust, you have to change this to like 75,000,
Yeah.
7,500 to 10 times the 3.
7.5 to 26.
So is this M
That.
Is this M dot minus or plus?
Which one? This is minus. On both sides is minus.
I definitely don't get the right answer.
If you plug in, sorry. You can use the TI-84 for the integral actually. You don't need to use
Remember, for the thrust, you have to change it to.
Yeah.
That's a 3.
Wow. Now you from 6?
Yeah.
Yeah.
And then I have to divide this by M naught, which is 400,000.
Minus.
Oh.
2,500 T.
It's yeah, over options
From
from
0.
60 to 134.
Alright. I feel like confident about that.
I'm not.
Yeah, I did not.
We get
2,131.
2,131.
I got-
That's the final Y.
Final Y, 2,100.
There's no way this is right. I got 2,857.
That won't be right because when you do this velocity, like you find the magnitude, it's going to be greater, right?
Yeah, it's way more.
Yeah, so that it has to be less.
Let me see. What did you put into the calculator?
Does M, no, so I was thinking, does it stop having, does it stop?
I'm just trying to count the zeros. That's fine.
It says 0
You
to
said 400,000. That should be okay. That should also be
So
okay.
then we did something wrong with the math.
Divided by root
Do you
2.
convert kilonewtons to newtons?
Yeah. And that's the mass times. Your integral is right.
Maybe the original integral? Because there was another integral before this, right?
Huh?
Maybe the 366.761. We can double check that one too, maybe.
No,
No,
this one is
that's-
fine. This one is fine.
That's fine,
Oh,
yeah.
okay.
400,000, 2,100.
But whatever you get for like this integral right here, you have to add that answer to this to get the final
Oh, yeah, you
velocity.
can do that. But that would just get you a bigger number. That's still wrong.
But it's in kilometers, not meters. The final answer should be in kilometers,
Our
not
answer
meters.
is in meters. We have
Oh, right.
2,800 meters. You convert that to kilometers, you get 2.8 kilometers. And the answer is 1.6
Yeah,
kilometers.
so we need, so this is considerably less, or this is a lot more than the actual answer. Did I drop?
I think we should double check.
Count the zeros.
Yeah,
I think we should double check from.
No, I think something's fundamentally wrong. Like,
Let me get
Someone can double check this as well.
Okay.
The first one. I'm pretty sure I did that one right.
but that wouldn't matter because these are too large regardless.
Oh yeah, we'll just do it just cause. I'll minus and not.
Did you use 400,000 as your M naught?
Plus, okay, m dot. Yeah, where? M dot is my minus. So okay. Please check if everything is right. Okay, I actually got 271.9 for that first value.
You did the integral?
Yeah,
From 0 to 60?
yeah. Unless you can check it again here, but 7. Like, okay, I'll tell you what I had in the numerator. The numerator was 7.5 times 10 to the 6th minus 8 parentheses. It's multiplying 5.5 times 10 to the 5th and 9.8. And then plus 2,500 times 9.8. Wait, is there a t after that?
Yes.
Okay, insert x. Never mind, that's right. 367 times 6 is about the same. Yeah. Okay. So
Try doing a time interval of 0 to 74.
why?
Okay.
Like a new reference frame. Starting at the 60 seconds mark.
So we said M naught is equal to 450,000 kilograms, but at 60 seconds you burned off 2,500 tons. Right, it is just a constant. But for this one you use M naught as this, right? For this one you use a new M naught because you burned off so much.
That's what I'm saying. For using a new M naught, you have to set it times 0.
What if that equation doesn't hold true? That acceleration equation
What
doesn't
is the
hold
y if you go from 0 to 70?
You get 591.
Really?
true? Wait, why is a y?
So what's you get 591 plus.
0.032.
Why is a y t
plus-
different for the first and the
Sid, what did you get for the first integral?
It's the same. 360.
Three-
Are you asking why these two are different?
Yeah.
Because the rocket changes to a 45-degree angle
Oh, right.
at 60 seconds.
Wait, I got the answer.
45.
I got the right answer.
Right. But also, it has the other
Literally,
stuff. Oh, but that's
Because that's always
Wait,
the
doing
easy
the
one.
time interval.
Works, it's a week.
Yeah.
So if you do the x and y integrals from 0 to 70 using an m naught of 0 to 74, using m naught as 400,000, you get 1.628 kilometers per second, which is the right answer.
Okay, wait. Walk us through how you got that.
Okay.
You can't do the integral from 60 to 134 using 400,000 because you're saying.
Here you go.
Oh. You have to do a new integral because you can't just start at time 60.
You're opting for 0 to 70.
You're given new functions that only apply at like a completely new frame.
Okay, but why 74?
Because that's 134 minus 60. That's like the difference, the time difference.
Okay, so so it's not the first 60 seconds, it's the first 74 seconds?
No, the first 60 seconds is right. That AYFT at the beginning is
Okay.
right. The second two have to go from 0 to 74, which is the same.
Oh, because that's the remaining time.
Yeah.
But why does it continue off from 0 to 74 rather than 6?
Because you can't say that M naught is 400,000 when you're starting at 60 seconds, because then by 60 seconds you'll have lost another.
You're doing a new frame of reference.
You'll have lost a whole lot of mass if you're going from 60 to 134,
Yeah.
and your M naught is 400,000.
That increases your velocity significantly. How we ended up with the same answer is kind of confusing to me.
Okay, but I don't get how it matches to go from 0 to 60 and then 0 to 74. Right?
What do you mean matches?
Like, because that's when the acceleration.
Like, just
applies.
imagine these two separate things. Your rocket has gone up. You're at 60 seconds here.
Because
It has
changes,
some.
You have to have a good frame of reference. So basically, your time starts
At 0 again.
Yeah.
Yeah.
For the other.
For your-
How do you-
for your
okay,
other
how'd you know
acceleration.
that? Just try things. And
Well, that's the only other way that it makes sense.
How did you
Like
know
those functions.
I want to know why the other one is wrong.
Because I thought about doing this like while I was doing the other problem, but it just like wasn't working out because I didn't change the.
Yeah, you have to change M naught.
So going from 60 to 134 is wrong because of the M naught.
Yes.
Not being,
Yeah.
Yes.
What it should be. What it should be.
So think about it this way: if your M naught is 400,000,
Yeah.
and you're starting your integral at 60 seconds, by the time you've reached 60 seconds, you've already lost that much of mass. So if you started at 400,000, that's exactly at the 60-second mark. That's how much mass you have. That's your M naught applied for the 45-degree angle of the rocket.
Okay. So the M naught is not 550,000, but the 400.
It's 400,000.
And that would be at 0, right? But if you put it at 60, it would be even more or something like that.
So we.
Okay.
I did
kinda
both
get
of those. You did the one integral.
Right.
I did my integral. Like I got I got 1,316.
Sorry. Yeah, no, sorry.
I got like 1,316 for the x direction,
Okay.
and you got 591 for the y direction.
Yes.
And I added 591 to 366,
Okay.
and then squared that,
Okay.
What did you get?
and then adding the 2 squares square root, I got the answer.
Cool.
You got.
This is for the x
Okay, I
direction.
guess that makes sense. So if you
And then
use
summing the y
60 to
directions, you get that.
134, that means that would be wrong because of M naught.
That-
Your M naught would be different than.
Well, this is
what
if
it
you
would
add
be.
the initial
Yes.
one as well.
You're assuming I'm not.
Yeah, so it's
You're assuming M naught was like stayed
957
at the 550.
It's
Instead of
591.
dropping.
it's 591 for just
yeah,
the
but if you
integral.
do 60 to 134, you're basically saying M naught is significantly reduced.
And then if you take
I
the
guess that
magnitude of
makes
those
sense.
two, well, you have to add. It's the same thing.
Oh. 957 what?
793. Yeah, and then if you take the magnitude of that, you get 1.628.
Right?
No,
This is right. That's the answer.
No, but 74, why are you taking 74?
Because that's like 134 minus 60.
Yeah. So you're using the 74 seconds, but you're not. The one difference we got from the longest right answer is doing the integral from 0 to 74 instead of 60 to 134. And the reasoning, I'm still not 100% on, but I think they know it's because of changing the frame of reference.
It's because of the mass.
the mass. Yeah.
See, it's just a question of being consistent. The expressions that are given are based on a particular reference. So you need to be consistent with that. That's all that there is. So there's a little bit of understanding. So I was really glad when you started off your problem by saying that it's a thrust and then the mass rate, the weight and things like that. Essentially, how it is coming as a acceleration is equal to force by mass, the resultant force by mass. So you need to be consistent with that approach in terms of what that is treating as the initial mass, and therefore the scale for T gets determined by that. Yeah. That's good. So as a team, you could do things much faster. I'm sure each of you individually would have been able to do it, but you would have probably struggled for much longer. So it really helps.
That's good. I didn't do this integral, and my answer came out to be like 1.3 kilometers per second. I was like, that's close enough.
Right. All right then. Yeah. It's. I actually posted the homework, but it was based on what I would have wanted to teach today. So don't worry about doing it by Wednesday. Thursday. So we'll have you presenting on Monday instead. Okay. Yeah. So you'll have a week. Yeah. Thanks. No. It's okay, because as I said, this is part of the learning process. So there are certain things in this which I would not have taught as part of the lecture anyway. So I would have gone on to things that are more important for your next homework. So that's why I'm saying, well, let's postpone the deadline.
Should we review these slides, or are you doing it next class?
Come again?
Should we?
Yeah, I'll do it. Yeah. But I'll do it a little faster now that I know you guys are much more aware of this. So I would have taken much more time doing this if your response today wouldn't have been as good as I saw it to be, because I anticipated it might be more at the high school physics level, but you guys have looked at things from a new perspective and looked at certain nuances in terms of, let's say, the acceleration not being constant, changing and things like that, and also applying it to a typical, there are a lot of assumptions here which are wrong, so as it's mentioned in the question itself for the rocket, but but nonetheless, from a dynamics problem point of view, I think it's the next level from high school physics. Great job, guys. Thanks.